Okay, welcome back to lecture 21.3, where what we're going to do is called the thermodynamic square. And this is a really nice technique to summarize all that information in a very tidy format and helps you remember it as well. Okay, it's very functional, and so we're going to go over the thermodynamic square this time. Okay, so it literally means draw a square. Okay, so we're going to use this square as a mnemonic, basically. So we're going to label it with our thermodynamic variables. Remember, our thermodynamic variables were S and T and P and V. So what we're going to do is we're going to have the extensive variables on the left and the intensive on the right. Now, which ones were extensive? Our entropy and our volume, and intensive was temperature and pressure. Okay, so we need to label these corners with our four thermodynamic variables. We're going to start alphabetically on the bottom. Okay, start alphabetically on bottom. All right, so that's going to be S and V and T and, nope. Go on my alphabet. P and T. All right. So we're going to see that our thermal variables are linked on the corners and our mechanical variables are linked on the other corner. So next we're going to label each one of the sides with the corresponding thermodynamic potential. Okay, so we're going to do it again. So these are my variables, my potentials. I'm going to do alphabetically. Okay, so let's remember what they were. They were U, H, F, and G. So let's put these alphabetically. They're going to be F, G, H, and U, starting at the top. Okay, so this is F, G, H, and U. And then finally, we're going to add some arrows. So add arrows, connecting corners. Let's say diagonally. Bottom to top. All right, so we kind of go bottom, top, bottom when we construct this. Okay, so why is this useful? Okay. So first, we can see that our thermodynamic potential is always cornered, right? Is basically sitting on a line or of a face whose corners are its natural variables. So I can say, oh, see, U is S and V, Or you tell me, oh, I want the natural variables for G. G would have been T and P. Or, oh, what is F? Well, it was T and V, or V and T. Oh, look, H was S and P. I just put the thermal variable first and the mechanical variable second. That's just my approach, but it doesn't matter technically which way you write that. All right, so we can get natural variables for potentials. But we can also use it to get our Maxwell relations. Okay, how are we going to use this to get our Maxwell relations? Well, we're actually going to write, I'm going to redraw it, my square here. I'm going to make it a little bit smaller. So U is, remember, I always just remember I start there, but what did we say? Extensive on the left, alphabetically, S and V, intensive on the right. So this was P and T. Bottom to top, alphabetically, F, G, H, and U. Add our arrows. All right, so to get our Maxwell relation, we're going to do the following. So I'm going to just pick arbitrarily at some point. Well, let's do two of them. So let's do the first one where we start here. So we're going to have basically, it's going to be like a 1, 2, 3. Okay, so 1, 2, 3. So we're going to go around the corners. So we're going to go 1, 2, 3. And what we're going to do is we're going to write our first partial derivative as basically partial 1, partial 2, at constant 3. Okay? And then we're going to come back at the corner that wasn't used, and we're going to go 1, 2, 3. Okay? And so that'll be equal, actually let's write that one in blue. So the first one will be partial, partial. So we're going to write partial 1, partial 2, 3, partial, partial, and that'll be red, and that'll be 1, 2, 3. Okay? So in this example, we did partial S was our first spot. Our second spot was V, partial V at constant T was 3, was equal to partial 1, that's P, partial T was our 2 at constant V. And remember, that is one of our Maxwell relations. It's the one for the Helmholtz potential, F. Okay, so remember sometimes we had a positive sign and sometimes we had a negative sign. And so how do I know if How do I know if there should be a positive or a negative sign there? Okay. Well, the answer is check. So here's my axis of symmetry along this, right? So here's my axis of symmetry, and if it's symmetric, then it's positive, and if it's anti-symmetric or not symmetric, it's negative. What I mean by is symmetric around my arrows, right? So my arrows both point up here, right? Okay, so let's do one more example. So one more use of my thermodynamic square. So again, let's just write it again real quick. Practice writing. I like to write it small. So S and V, P and T, F, G, H, U, arrows. So let's do a Maxwell relation this way. So that was 1, 2, 3, and then back 1, 2, 3. Okay? So this will be partial V, partial T, a constant P, right? 1, 2, 3. And then we have partial S, partial P, at constant T. But now let's look at this symmetry. So here now my line is my axis of symmetry for these two would be here, but they're not symmetric. When I flip it, my arrows would go the other way. So I have a minus sign. Okay, so you can see this is basically captures all of that information we had in the summary, but in a very quick way to do it, right? So if I write my thermodynamic square, I can get my Maxwell relation really quickly. So you'll remember that this was the Maxwell relation also for G, right? When we derived it from G, which makes sense because this is the one it's symmetric about, right? The arrows are pointing and overlapping. Okay, great. So in class, we're going to do a very extensive example where we're going to squeeze a liter of mercury and see what happens, okay? And we're going to need to use one of these Maxwell relations to do that derivation, okay? So that is in class. See you there.